Sorry, everyone. We had some technical difficulties. For some reason, I couldn't start the GoToWebinar, so we just figured it out. We'll get started in just a minute. All right, everybody. How's it going? My name is Chris Small. Apologize for all the colors. I was doing this with my 7-year-old daughter, apparently. It is Easter week. I like Easter. I like holidays, so forgive me. I tell my counterpart Stu, he's always got these professional-looking webinars, and I guess I have to start asking him for help but I still like the holiday theme. So anyway, we're going to be talking about resistance grounding in the renewable space, why it's best ? Basically, we're trying to kind of tell you that is it really best? What's the best way to go? At the end of the day, I think it's situational, so we'll go over that as we go. My name is Chris Small. I've been a post-lover for, now I think it's 13 years. I should update that. I graduated from Ohio State. Is that on? Yes, sure. Graduated from Ohio State. Okay, looks like everybody can hear me. Sorry about that. There we go. And with an electrical engineering degree and regional sales manager, application engineer. But let's move on with the topic. So today we're just going to go with an introduction into renewables, some grounding methodologies, kind of a review, kind of some pertinent methodologies. Sorry, we're still having some difficulties here. It's been a rough day, technically speaking. Hopefully we'll fix it soon, but hopefully you guys can still hear me. Go into some grounding methodologies, some of which will be review, others may not be for some of you. Just basically pertinent to the space. Application comparison, talk about utilities and their role in the process, do a little cost analysis, and then end everything. So let's get started. So we have renewable energy. Overall, the sources, this is from 2020, it's straight off their website. It's probably the latest data, considering it's on my front page. I'm assuming it's the latest data that they have. So renewables make up about 20% of overall power in the United States. You can see kind of the breakdown. Natural gas is the most. We don't need to kind of go into there. I was actually surprised to see coal down 19%, but I think we all know that that's been an effort here recently. So in terms of renewables, you look at wind, hydro, and solar. Those are your major subsets. I would say, obviously, you look at the. So let's move over to here. You can kind of see here that in terms of renewables, wind is a little bit just recently eclipsed hydro. So I mean, when I think of renewables, just to be honest, sorry for any hydro guys out there, but I think of wind and solar. But obviously, hydro plays a significant role. Until recently, the most major role. But the point is that those two are probably wind and hydro are obviously the vast majority of your renewables. And of course, these are increasing, so they'll continue to play a larger role. So let's go into just some difference. What you will see, what you would potentially see on your renewable systems. Ungrounded system, just to go over as a review, you have the you have your no intentional ground path. You have your system's capacitance through here. The reason why I bring this up is because this is kind of the situation where the over voltages are the worst. You have up to 8 times your rated voltage due to potential intermittent faults, especially in regards to renewables, especially when you have long runs, I should say, on your neutrals for your sources. A little longer, the more likely, I would say. I don't have any data on that, except for the fact that it's specific data. I mean, but it's just a kind of a known thing. But anyway, so when you have intermittent fault, go through here, the system's capacitance charges up, and that's what over voltage is the system. That's where you can get, like AAA talks about, 6 to 8 times what you're talking about, your nominal voltage. That's a lot. That's 3,000 volts roughly, 3 to 4. So that's a problem. So really, ungrounded systems, over voltages is the problem. We can really move on. I'm not going to belabor these. I just want to kind of go over this, especially for people who don't haven't seen this before. So I'm just going to throw resonant grounding in here. I'm not going to talk too much about it. I did want to give it a hat tip because it was in a lot of research that I did had resonant grounding in there. I don't know exactly why. It's actually theoretically a good solution. It's basically a reactor with essentially a tunable. You can tune it to basically offset your system's capacitance, and therefore theoretically that would be great if you could operate under that scenario. However, it's very inflexible. If you're doing switching or you do any modifying your system, you're going to have to retune the coil, and this becomes kind of impractical for most applications. Now, if this fits for you, by all means, it is an interesting application, but it's kind of it's very limited to what you can do with it. Of course, you move on to solid ground systems. Generally speaking, industry-wide, I mean, usually you see, or especially in like commercial, it's in a lot of industry, you see solid grounded. It's not ideal for renewables because of the high fault currents. So because of the low impedance, you have these high fault currents that can occur. Arc flash, arc blast. As you can see, the third book talks about how you get severe arc flash burning from any phase of ground fault. So we really need to think through where we use solid grounded based on that stuff. It does well at finding the fault, clearing the fault potentially, because there's a high level indication potential there. However, it can cause damage. It's the arc flash capability. The arc flash probability is higher because of the amount of energy, etc. Moving on to effective grounding. We need to talk about this because this is important in the renewable space, especially with wind and solar. It is essentially the same thing as solidly grounded, except you're going to have some kind of impedance. So it's basically a low impedance path, but it's not as low as solidly grounded. How the Green Book defines it is essentially you have your zero sequence reactance over your positive sequence reactance. Really, this is kind of more for reference. We don't need to talk about how you achieve this, etc. I mean, well, actually, we will talk about it in a general sense. We won't talk about it in a technical sense. But so you get the idea here. When you achieve this, essentially you're going to, in terms of voltages, in terms of currents, you're going to get about 60% of your three-phase short circuit current and about 100% potential over voltage of your nominal voltage. So it's better for sure than solidly grounded. There are some limitations. Obviously, these are still high numbers, so there's still issues that can happen. But they are limited, relatively speaking. In terms of how we practically use effective grounding, a couple of different ways. First is to use a grounding impedance. In this obviously this picture is an example of a reactor with a solar application. So essentially, it's just an inductance. Once again, that kind of it plays with the I guess the y-axis or the imaginary part of your power, and it can balance things out. It can create, or I should say, lessen voltages, etc. So that's one way to do it. It's actually slightly more expensive than the other way we're going to discuss, which is the grounding bank. I think a lot of I see this a lot in renewable applications. Usually it's a transformer. We get a lot of requests for zigzag transformers, which, by the way, just from a sales perspective, we don't actually provide those by themselves. We provide those in packages. But the point is that your most common way to have what's called a grounding bank, there's a couple different transformers you could use. You could use Y delta or a zigzag. I just put the zigzag here. It's more efficient to use a zigzag. You're going to need. We don't have enough time to go into how you size those, but if you look at the different ways you size them, you would find that zigzag is actually a little more efficient. You're going to get a smaller zigzag for your buck. So yeah, so those are kind of the two major ways to do it. You can obviously use a transformer as well, typically with the inverter. So I guess there's three, but I displayed two. So that's effective grounding and how you achieve it, and what practically you would use with it. So like I said, if you have any questions with sizing, we can definitely talk about that after the fact. But yeah, there's definitely some equations for that. Okay. I felt like that went fast, but first poll question. As you look at, it's not my dog, it's I like the outfit though. While I'm waiting, and Stu reminded me, so I appreciate that, Stu. Oh, so if you guys want to ask questions, you go ahead and list them. There's a question section. Stu will be looking at those and either answering them for you during the presentation, or we will bring it up after the presentation. So please go ahead and do that if you have any questions. We're kind of doing a top level view of this. There's a lot of information in this category, so I had to kind of do a top level. But we're definitely we'll be willing to answer any questions you guys may have.
As a first note, we are aware that there are potentially some audio problems. We are looking to rectify that as best we can. To summarize the poll questions at this point, 37% of people have indeed run into utilities requiring this, and darn close to 50% have not worked on a solar wind project previously.
Okay. Sounds good. Thank you, Stu. Let's move on. I apologize for hopefully you guys can hear. Okay. So let's go into resistance grounding. Essentially, you have just a neutral between resistance to ground. Excuse me, that's not right. You have a resistor between neutral and ground. Similar to a solid ground, except for you're achieving a couple things when you put that resistor there. Number one, you are engineering your ground fault current. So if you want it to be 10 amps for example, high resistance grounding, you could use a 10 amp resistor there. The one caveat in resistance grounding, or I should say that there's not one, there's actually a couple, but the one we'll talk about right now, in terms of design considerations, you need to make sure that your resistance value or the associated current of your resistance value is higher than the capacitive charging current. So remember when I said that your ungrounded systems have you have a overvoltage condition here, but you also have the current associated with that that's leaking the ground essentially. And it's simply very small, but you need to make sure that this resistor here has a higher current, basically the path of least resistance. You have more flow through here. Therefore, you don't have this overvoltage situation that you would with an ungrounded system. So that's the main issue you need to solve when designing something like this. In terms of the IEEE, Red Book talks about how there's no arc flash hazard. That's a little bit too short of an answer. There's no arc flash hazard for ground faults. So that's about 98% of all your faults are lined to ground, roughly, give or take a couple. So for those faults, you have no arc flash hazard. There's not enough voltage to create that arc there. Then also you drastically lower your current. Once again, you're engineering that. And you're able to do both those things. Essentially, it takes the best of solid grounded and ungrounded systems and kind of gets rid of the bad stuff. That's kind of how I like to think about it. So overvoltages are reduced, really talking about straight ground currents. Move on from there. Two different types of resistance grounding. There's low resistance grounding and high resistance grounding. Let's talk about low resistance grounding first. Typically, it's almost always at medium voltage, 2.4 to 35 kV. Really, the sweet spot is between 5 kV and 15 kV. You could do that range. You could do actually higher than that if you'd like, but it's most common there. And then once again, we see the vast majority of our applications are 5 and 15 kV class at least. 25 amps to 1200 amps. Once again, you could go higher than that if you have like a lot of imbalance or some large application where you need a higher current, but it's not that typical. Your sweet spots, once again, at that medium voltage ranges could be 200 to 400. Typical ratings are for 10 to 60 seconds. This is for low resistance ground. 10 seconds being most common. You're essentially going to be tripping on a ground fault. You're going to segregate the system, that portion of the system, and then you're going to obviously go offline. But one of the or several of the reasons why we use low resistance ground. One is for equipment protection. You're going to be, once again, you're going to be lowering the amount of current that flows, especially well, really compared to either one of the I should not say either one. I should say the effective or solid ground systems. Comparatively to that, generators, they're used often for generator protection. We'll go into that a little bit. Relay coordination. So if you lower the amount of current that flows, then you're able to coordinate better. You have more time because your system can operate longer at a lower current, and so therefore you have more time to coordinate properly versus trying to basically instantaneously trip and potentially tripping your entire system offline or a larger portion than you desire. Of course, you can ride through transient faults. This is typically a few cycle faults or something like that may cause you to trip. Typically, this would allow you to be able to ride through that. So that's really, in terms of application, medium voltage application where a generator or other rotating machinery are used. That's true. There's others as well. We'll talk about that in a minute. But that's kind of the bread and butter of what we do. But yeah, there's other possibilities. High resistance ground. Moving on. I'm sure most of you are aware, we're just going to continue this review. Essentially 480 volts to 5 kV, 0 to 10 amps. So 40 volts is the most common, it's low voltage. You're going to be continually operating typically. This is the level. Well, really, when we talk about high resistance grounding, usually we're talking about continuity of service. So we're looking to not trip on a fault. We're looking to just alarm. So that's one of the three major reasons. Arc flash mitigation, especially at low voltage. I've already mentioned it before. Electric Waste talked about how there is no arc flash potential on your ground faults. So you get the idea there. There was a paper that was done a few years ago. I'm sorry, I cannot quote it for you, but essentially the bottom line of it was about 95–97% of your arc flash is mitigated. Potential is mitigated. It doesn't, just to make sure I'm clear, that doesn't actually mean anything in terms of arc flash gear or category, because your worst case is still there. But in terms of the number of events or the possibility of events, it's drastically reduced. And of course, if you're operating very low current, the equipment protection is something that it affords you. Applications quickly, we're really talking about, just generally speaking, we're talking about data centers, oil and gas, water, wastewater, hospitals, food, any kind of batch process for industry. And we do renewable. I will say, just to be honest with you, we do a decent amount with hydro. We do a decent amount, especially we did a lot before. We still do a decent amount with wind, and we do a little bit of solar. We don't have a lot of requests for solar, just to be frank. There's probably some reasons for that we can talk about, but doesn't mean you can't. But anyway, so that's kind of the idea of your applications. Yeah, this is well, they got a download problem. That might have been part of our technical issues. I apologize. Hopefully that's the only one. We'll go with that. Hopefully, there is supposed to be a hydroelectric dam there with a rotor and a just kind of showing you the system, with the turbine, etc. Essentially, the bottom line is that, and I can't promise this for all hydro applications. I'm not honestly a hydro expert. I definitely, like I said, we've worked with a lot of these types of applications where we have just essentially a generator with a turbine and some moving water, and you're generating electricity. That's kind of what we do. We do here quite a bit. This acts essentially like a generator, your typical generator. So to talk about that, in terms of generator protection, most of the time, your medium voltage generators are going to be protected by a low resistance ground system. The reason for that is, generally speaking, medium voltage generators are not braced properly for ground faults in this situation. They're braced for three-phase faults, and you'd think that that would be sufficient, but it's usually not. That's why, like I said, I truly recommend that. And so they do recommend resistive or reactive. I'm not going to go into detail of that because we've done a presentation on that before. But the gist of it is, most of the time you'd use resistance ground. I've seen IEEE white paper discuss about 95% of industrial applications you'd use that. Now for higher voltages, we're talking 35 kV range and above, or potentially lower depending on the current you want, or you need, I should say. You would use reactive. It's a much higher ground fault current, but it's more cost efficient at higher voltages. Okay, just some some more details about generators, mean voltage. I want to just touch briefly on hybrid power, or resistance grounding, I should say. Not hybrid power, sorry about that. Hybrid resistance grounding. Essentially what you have is the first illustration you have here is you have your potential internal fault from your generator. So when you have an external fault in your generator, everything works as you would expect, as I just laid out for you in the previous slide. But when you have internal fault, essentially you're going to have to wind down after you trip, and this is what you're going to be getting. And this actually causes, there's a couple white people in this, and it goes into detail why this causes a lot more damage than you would expect. But essentially this causes additional damage. So hybrid application would rectify that issue. Now, I bring this up because once again, this is ideal for generators, medium voltage. Could very well be a good application for your hydro application. I will say this, generally speaking, this is, like I said, this is gonna be high level. Application-wise, it's very varied. I guess I'll just say a general statement. I'm gonna look at every application like it's completely different, because you know, do you have step-up transformers? What's your voltage is? Where are you stepping up to? All kinds of different. How is your array situated? Do you have multiple generators? Are they parallel? I mean, you guys know. There's a lot of variables. So you know, we just look at a one line typically. So we don't really have a one size fits all solution here, but we're just kind of go over some general principles, and hopefully that helps you decide on what you would like to use. In terms of finishing off this point, the hybrid grounding single generator, kind of on the right hand side there. You have an LRG and HRG in parallel essentially. This is, like I said, single generator. What happens is you have a high speed disconnect switch here. This is actually quite in depth, both for the relay and get some differential relaying to help figure out if you have internal fault here, and then you have some harmonic filtering, potentially over voltage suppression as well. So with all that going on, the bottom line is when you get an internal ground fault on the generator through your differential relay, you trip or you open your LRG, and you're basically winding down with that, whatever this is going to be, 5 or 10 amps high resistance ground system. Or really, it's typically just a resistor in this scenario. It's not actually a system. But you get the idea. So that's a single generator. To finish the point in terms of what it looks like, this is a common application when you have parallel generators. You have your zigzag transformer, you have your 400 amp 10-second LRG, which hangs off the bus, and then you essentially have an additive ground fault current, 440 amps for a load side fault. And then if you have a generator, internal generator faults, you would essentially detect it once again through the same type of relaying I mentioned. You would open your breaker and wind down separately and safely at 10 amps. So that's kind of the idea. That first slide I showed you, where the first graph that talked about the extra damage, that would take care of all that. So I just want to bring those two possibilities. But that's big. So I guess I didn't really give you an idea. Hydroelectric power is, once again, just like a generator. So I would treat it. The reason why I bring this up is because generators, medium voltage, we almost always use resistance grounding. If you have the ability to calculate the fact that your bracing is sufficient for your generator, you don't have to, or I should say, it means you don't. It's not recommended, or the recommendation no longer applies. Essentially, that's the reason why the recommendation is there. But most of the time, you're gonna just go with, in my experience, at least, you're gonna go with the recommendation for a resistance ground. And since a hydro is in that category, I would do that as well. Now, I guess one thing that might be different is the voltage level. And we'll talk about that later when resistance grounding becomes less viable and maybe reactive grounding becomes more viable. I'll talk about that in a second. One thing I do want to mention is for utilities, this is kind of not really an afterthought, but it's kind of one of those things where it's not a big part of the technical issues, but it's a big part of the application issue, because a lot of times utilities, they have transient over voltage, that's a TOV. They have to worry about potential over voltages when they are working with most likely a wind or solar application. And they need some kind of lower voltage protection. I mean, typically this happens like in an islanded situation where you have ground fault. You might have some over voltage problems there, and that could be seen by the utility upstream. So there's some examples of utilities that have some over voltage protection there, and that's how they kind of give their customers more freedom to do what they want. But there's also utilities that, because of this point, they require you to effective ground, which we just talked about. So you need to know, this is kind of an important point. I know even if technically speaking, there's some benefits and some good things to do to achieve with resistance grounding. If your utility is not going to allow you to do that because of their protection, that's a problem. So I just want to make sure you guys are aware of that. You need to check to see what they require. So moving on to wind power. Essentially, so a couple things. Obviously you see there's a way you can resistance ground wind power. We used to actually do this a lot. I would surmise that the main reason we don't do it as much anymore, we used to do this, this was probably with some of our bigger accounts, was with wind power. We still do, like I said, we definitely still do wind power, but we used to do a lot. And I think the main reason why we don't is because of the voltage levels that have potentially changed, and the higher they go, once again, we get back to the point where the resistors become expensive. And so I cannot argue with the fact that effective grounding is typically cheaper, although sometimes it's negligible in terms of the difference, but it really just depends on, like I said, the voltage and the current that you're looking for in terms of the resistance. So just in terms of some benefits in this application for resistance grounding, just make sure, just in case just before I start that, just in case wasn't clear, the effective grounding is essentially solid grounded. There's some benefits, and we'll go over those, but it's very similar to that. It's allowing those over voltages to be somewhat suppressed, and so that's kind of the difference. But that being said, resistance grounding, if you need continuity for your wind power, that's unique to resistance ground, specifically high resistance ground typically. And then you have your arc flash reduction. We've already talked about that. You can have downtime and equipment down because of arc flash. I mean, that's part of it. You definitely want to be able to reduce that drastically is a big positive. And then once again, I've already said that. So basically, so there's a couple different variations. There's all kinds of different variations. You can do parallel generators, but in this application, you have single generator transformer. You can do parallel gens to a single transformer, and there's all kinds of things you can do with this. Just an example of being able to ground at different levels. You can obviously ground, your generator. You can do, for example, a high resistance ground system here. We definitely would recommend medium voltage at your we would definitely recommend low resistance ground at your medium voltage. Really, anything above 5 kV, there's not really a good case for high resistance grounds. I guess especially in the type where you continue to operate. There are some applications where you would use that for just generator protection. You wouldn't necessarily be operating continuously, but the point is that usually 5 kV and below is where that's at. Anyway, so the point is that up to, even at the higher voltages in this picture, you talk about 36 kV, potentially you could use it. So move on from that. Let's go to poll question number 2.
Wow, this is not even close.
I'm guessing that, I think that marshmallow money should be banned. So does people agree with me, or?
People are, yeah, other than 12% of people who will find you later and ask you very pointed questions.
Yeah, I'm sorry. I didn't mean to call you guys out or anything.
But yeah, it sounds like peeps are just not the go-to.
I was gonna say peeps, but that, yeah, I thought I'll stop at the marshmallow bunnies. Those are kind of Easter themed, but anyway, you get that. Yeah, peeps, I guess, would have been the more recognizable term.
So yeah, 87% of people are definitely thinking chocolate bunnies.
I agree. Okay, good. Moving on. Solar power. So just I want to spend some time on the grounding methodologies, especially effective grounding. And because of the fact that you can get into the weeds with all the different applications and how there's a lot, there's very different. I kind of just more generally going over the applications because I really do think that it's really case by case basis in terms of what you have. Obviously, but from a cost standpoint, that is the case for sure. I've already mentioned that solar is not, I'm not going to pretend like solar is a common application. I don't know if it doesn't, not that it doesn't have it, not that it can't be. I believe, based on my research, and maybe others have different opinions, but there are potential over voltages that can be caused by resistance grounding, similarly to ungrounded, although not to that extreme. We're talking about the not the necessarily capacitance kind of running like a runaway train out over voltage. We're talking more about just the non-faulted phase voltages going upwards of a line voltage. That's what I'm referring to. So in that scenario, I could see where it might be more complicated to have that resistance ground with your equipment. Now that being said, we do solar applications. So I just want to be, honest about it, because just because we're not doing a lot now doesn't mean we can't. I'm just trying to figure out a reason. And that's probably the biggest reason I can think of, other than utility. Obviously, utility is a big reason as well. If they tell you that you have to effective ground, then I'm guessing you effective ground. I did a lot of reading about lightning. In fact, I would say that a lot of, especially when we talk about wind power. So obviously wind turbines are very susceptible, especially the big ones, to lightning. To a lesser degree, obviously solar, they're out in the field, but they're much lower than the ground typically. Now if you have on top of a building, that might be a similar issue. I just wanted to kind of share what I found. And the reading that I found, basically, they refer to grounding and bonding. And so typically in my experience, what they're referring to is actual resistance of the ground connection you have to earth and your ability to get a good low resistance ground for your ground rod and your ground ring. There's a lot of papers about that. I just, talk about bonding, equipment ground, et cetera. It's not really the same thing as system ground. I just wanted to, if you look at renewable papers, you probably find a lot of them on lightning. And I would guess that has a lot to do with, there's a lot of issues with wind turbines. And of course, you're going to need the additional protection, source suppression, et cetera. But from what I've read, there's a lot of times those don't even work when you don't have the proper grounding. So just wanted to bring that to your attention. In terms of grounding comparison, this is just kind of looking at overvoltage. Really when I talk about different groundings, I really focus on overvoltage just because you have that with ungrounded systems. We already saw that on Triplet quote. Overcurrents, obviously, we have that as well. And then our flash is kind of a symptom of that. But the just as a breakdown, you could get, once again, 16 times your rated voltage. That's why that red box is there for the ungrounded. You typically don't have a lot of current there because your impedance is high. You don't have a purposeful ground. It's like, it's air and it's insulation, so it's going to be low current there typically. Our flash is typically reduced. Now I will say, if you get a system failure because you have the overvoltage condition, all bets are off. But in terms of a ground fault, your first ground fault, at least you're not seeing that as much. Solid ground is kind of the opposite. I didn't have an exact number on the voltage, but essentially it's the lowest of all the comparison. And your overcurrent, just obviously by design, this is designed this way. It's designed so you can have an extremely high current with relays, able to see it very easily and trip offline as fast as possible. So by design, it's extremely high. And because of that, the arc flash is bad as well. Effective grounded, hopefully you guys, if you guys haven't seen that before, effective grounded, it's kind of, it's trying to solid ground without solid grounded, essentially, I guess is what I would say. So you have a lower current. You're reduced to 60% of your three-phase short circuit current. Your voltage is a little bit higher, but still acceptable, I believe, especially for a lot of certain electronics. 140 should be okay. So once again, there's still a lot of energy, a lot of potential for arc flash. Or resistance grounded, the voltage is usually not an issue for for other applications. It's not as much of an issue. You still have to worry about some piece of equipment for low voltage, not wire, but more like surge pressors and stuff like that. How you hook them up, what they're rated for. I mean, voltage is going to be different. But that's where you want to worry about is for wind and solar. You're going to worry about that voltage there. Your overcurrent it's not an issue. It's engineered. So if you engineer it correctly, you should not have much issue with that. So if you want to be 10 amps, it's 10 amps. That's my point there. Then our flash, I've already mentioned that it's highly reduced. Hopefully this is a clear visual. I could have put a bunch of references here, but I figured it was pretty simple to figure out. Green is lower cost, yellow is kind of in the middle, and then a red is prohibitive. This is just a cost consideration. I wouldn't necessarily recommend some of these values. I don't necessarily, some of these are impractical in terms of application, but from a cost perspective, I want to give you guys an idea of the range of what we could do. and what it would look like. So when I talk about, you're going to probably be using a reactor, or you're going to be using a zigzag instead of a resistor. A lot of the times it's because of these red boxes. We read a voltage where it's more prohibitive to in cost and size to use a resistor, and so the benefits aren't necessarily worth the cost potentially. So this is where we see issues with resistance grounding for both generator protection and larger application. And wind solar, a lot of times, the common values, we go from 690 volts, all kinds of different voltages, 6.6 kV, all kinds of different values. But once you're getting to the 20 and 30 Ks, which is not that common, that's when it starts to become more difficult. So I just want to make sure you guys have a good visual of what that looks like. There's a lot of different pricing here, so I don't want to go into specifics, but this gives you a good visual for what the costing looks like, and what I would consider green basically negligible in terms of the cost of your project. It's obviously it's very, very small, but then this gets much higher than that if you have a large current and voltage. One thing to talk about on medium voltage, the cable installation. This is just kind of going along with what I was saying before. You need to make sure you're properly rated. If for solid ground, you don't have to worry about it. Low resistance ground, you don't have to worry about it. But if you were talking about high resistance ground, like I mentioned, like I said, there's costs associated with having to be able to continue to operate, especially medium voltage. So you need to look at these values and see if it's something that's you're interested in doing. But yeah, you have to do that because, for example, continuous rated, you're definitely multiplied by square root of 3, so that's 173%. So that's where that other number came from as well. Other considerations as well. A lot of times when you have larger systems with larger voltages, you see a lot of times you have a certain percentage of imbalance for a 5 kV transformer. That's going to be extremely small. If you're talking about a huge transformer, it's over 15 kV or 15 kV with a large service, 1200 amps, whatever it's going to be. The potential for imbalance can be greater. So you need to worry about that as well. It's another consideration you need to worry about. If you have a lot of continuous current, now if you have a significant amount of imbalance in terms of percentages, 5 or more, I would say more than 5%. Some people load 10%. I think that's way high, but that's their call. But the point is that if you get a lot of continuous current, that's going to make this harder as well, because you're going to have that additional continuous current flowing on top of the ground fault current, which you'd have to be able to handle both of those at the same time under the same temperature. So in conclusion, I want to just talk about the fact that we have, I think the most important thing is to differentiate the types of grounding instead of going through applications, because that's kind of secondary. If you can understand the different types of grounding, how you achieve them, then and the benefits, and then you'll kind of know what the benefits you want, and then you can go to application restraints or utility restraints, etc. So that's the start of it. So the conclusion of resistance grounding is common for hydropower applications. We do them a lot, like I mentioned, especially at low and medium voltages, more so medium, but also low. Arc flash reduction and continuity service relay coordination are clear benefits of resistance grounding. That's really why you're going to want to be using it. If those aren't something that you are interested in or not as important to you, especially for your renewable application, you probably won't want to use it. That's usually why a lot of the main applications or process, and downtime stuff, anything with downtime or process, That's a lot of high resistance ground applications. Then low resistance ground, once again, is coordination, et cetera. This must have cut off here. Renewable energy grounding. You know, you want to make sure. I guess the bottom line is you want to kind of prioritize what's the most important to you. Do you have, is continuity of service most important to you? Is arc flash reduction most important to you? Is obviously just, you know, working with the utility if there's a lot. We have I know of several utilities that already have over voltage protection, so you're not required to use effective grounding. I think it's unfortunate that some utilities require that. At the same time, I can't blame them; they're protecting themselves in probably the easiest way if not possible. But that's the point. I guess when you talk about renewable energy grounding, you're going to kind of go with the type of grounding first, and then kind of work your way backwards. Okay, so yeah, I apologize, guys. There's not too many issues, but there's a few issues with this presentation. We'll clean them up before. I think it must have been a bad download. It might have been part of our technical problems too. But if you want to contact me, which is the slide that's missing, chris.small@postflower.com. And we'll be doing another presentation next month. If you guys have any questions, we'll answer them now.
There were actually no additional questions. There were some comments about the microphone that I addressed, and somebody did point out earlier on one of your slides, the slide, I guess, said there was, and I assume it was on the resistance grounding slide, there is no arc flash hazard. And of course, the talking point was there's no arc flash hazard from a line to ground fault. Obviously, if there's a ground to ground or a line to line fault, there could be an arcing event.
Yeah,
it's not addressed by
it was probably not the greatest idea, not because, well, I addressed it clearly in the presentation. However, the problem is if somebody's going to be reading this later, yeah, they may get the wrong impression. But yes, that's clearly for, and actually the way they say it in the IEEE as well, they make it very dogmatic like that. However, the context is for line to ground faults. All right, guys, I really apologize. This is all the technical issues we had. Unfortunately, sometimes it happens. So hopefully you guys got something out of it anyway, and we worked through it. And I appreciate your time, and we'll see you next time.